So that in and of itself isn't very helpful. Let's expand that. Expanding this, initially, we have kinetic energy. We also have potential energy. And in the end, we also have kinetic energy, and we also have potential energy. And you're saying, well, how do you know that? Real easy. If you're moving, you have kinetic energy. If you pick something up against gravity, you have potential energy. Now, in our next unit, or next week rather, we could make this more complicated. We could also have work initial and work final. And what does that mean? It just means that if you push or pull on a coaster. So for example, like on the start of a ride, like on Batman or Raging Bull, to get the ride going, there's like a piston that pushes the carts to get it moving so the chain dog can grab it. That's work. At the very end, usually they slam on the brakes. That's work final, to push against the coaster to slow it down. You see that? In our case, we're not worried about work because we're not given any information about the coaster getting pushed or pulled on. So now let's expand for KE and PE. How do you find KE? It's 1/2 what? mv squared initial. How do you find PE? mg what? H initial, and that's equal to 1/2 mv squared final plus mgh final. Looks scary? A little bit. It's not too bad. It's just shoving a bunch of numbers. But you know what? Let's make your life easier. You guys look tired. One little trick. What can we do before we shove in numbers? Good job. What can we cancel out? Algebraically, what's the common term that all the terms have? I heard it. Mass is the only variable you can cancel out. Someone's like, cancel out G. You can't do that because KE doesn't have G in it. But everything has mass. Therefore, what's kind of cool is it makes the math easier. Also, what does this mean? It means that in real life, what falls faster, heavy thing or light thing? In the absence of air resistance, all objects, Galileo discovered, will fall at the same rate of acceleration. So when we go to Great America, you wait in line for Raging Bull, whatever, time it. A bunch of junior high kids on a field trip from Michigan get on. They get off. 47 seconds. Bunch of football players, they hop on. 47 seconds. Same. In other words, yes, mass makes a small difference, but you compared to a giant coaster, right? You compared to the Eagle, Raging Bull, not going to be a big difference. Into our equation, plug and chug. Here we go. So this reduces to 1/2 initial velocity squared. What's VI? 2.1 meters per second squared plus the potential energy, which is 9.8 times the initial height of what? 120 is equal to 1/2 VF squared. What do I put in for VF squared? Oh, wait a second. That's what we're solving for, right? VF squared plus G, 9.8 times 60. So all I'm doing is just substituting in all my info from step 2 into step 3. That's why I want you to write out the equation so you don't screw up the algebra where the numbers go. So let's get out our calculators. You get out yours, I'll get out mine. I'll race you. You'll win. There you go. Left-hand side, we're going to take 1/2 times the initial velocity, 2.1 squared. Add to that sucker 9.8 times the initial height of 120. When we do that, we get a big old nasty number, 1178.205. Keep the decimals for now. Round it at the very end. That's equal to 1/2 VF squared. And then we're going to do 9.8 times 60 on the right-hand side. And we're getting a big old number, like 508. So algebraically, how do I get VF by itself? I need to first do what? Subtract from both sides what? 588. And then to get rid of this 1/2, we're going to multiply that by what? By 2, right? And then take the what of the whole thing? The square root. So what we're going to do is take 1178.205 minus 588. Multiply that sucker by 2. That was 590 point something 205. 2 times that to get rid of the 1/2. And then take the square root of the whole thing. When all is said and done, we get a final velocity of like 34.36 units. Super important. What are the units? Miles per hour? No. Meters per second, which is roughly over 75 some miles an hour. You multiply by 2, 2.24 to be exact. So using common sense, is that reasonable? I think so, right? If we start off at 120 meters high with an initial speed of 2.1 meters per second, you fall down a 60-meter hill to 60 meters high, you're going to speed up to about 34.36 meters per second. Extremely reasonable. Big picture, what do? We visualize the energy transformations that we put into our system in the pi, what we got out. Step 2, that was the hard part, breaking all down, the knowns and unknowns. Step 3, we expand the energy equation for conservation, and then we substitute and solve. As simple as that.